equilibrium, you can just go into your ice table and like solve that value that you and that. If you know the concentration at equilibrium, we would plug it in for the equilibrium value, the one at the bottom of the ice table. So if you're asking a question that comes from the homework someplace, we can look at that one after this. Okay. More than happy to. All right, so it looks like our initial concentration of COCl2 is 0.3166 molar. We're doing 75A and repeating that for the recording. After this would be number 77. Now look at the K value for 77. That is not a super small number at all. So because it's not a small or a really big number, we're probably not going to be able to use them as simplifying something when we do the calculation for number 77. Yep. I mean, it can be quadratics. It can sometimes be cubics or even bigger. But we use graphing calculators to solve anyway, so it'll be fine. Our initial concentration of COCl2 is 0.3166 molar. Our initial concentrations of the products are 0 molar. To get to equilibrium, what's our change going to look like here? And on the reactant side, minus X. Yep. And the reason why 1X change for each of these is because it's a 1-to-1-to-1 mole ratio. Remember, if we had a 2 or a 3 coefficient there, then our change might be a 2X or a 3X instead. All right. So at equilibrium, our calculations say that our final molarity of COCl2 should be 0.3166 minus X. And our final molarities of carbon monoxide and Cl2 should each be X. Our K for this reaction is 2.2 times 10 to the minus 10. And if we write our general form for that equilibrium expression, we know that K sub C should equal our molarity of carbon monoxide to the first power times our molarity of Cl2 to the first power divided by our molarity of COCl2 to the first power. We all good so far? And then we substitute in everything that we know from our ice table, all right? Our K is 2.2 times 10 to the minus 10. And that should equal X times X divided by 0.3166 minus X. Here is where we can simplify our lives by using that simplifying assumption. All right, so let me state why we can do it one more time so you understand. We know that this equilibrium constant is a really small number. What that tells us is that at equilibrium, this reaction should have almost 100% reactants and almost 0% products. A really small K means that we have almost no products at equilibrium. So because of that, we know that 0.3166 minus X is likely to be very, very close to 0.3166. In other words, we don't need to make much of a change from where we're at right now to get to equilibrium. So how does that benefit us? If we can say that 0.3166 minus x is approximately equal to 0.3166, then our calculation gets really easy. So x squared over 0.3166 is equal to 2.2 times 10 to the minus 10. Here's how I would solve that using my ancient, literal, antique graphing calculator. Who knew in the digital age that we would have antique graphing calculators? But this one has been around since like the early 80s, which is antique at this point for a piece of technology. All right. So somebody like finished playing Pong on their cathode ray tube television screen and then sat down to do calculations with this thing, which is awesome. All right. So I would do 2.2 second function minus 10. Remember that is TI calculator notation for how we handle significant figures. Here's the EE button right there. All right. So second function and then that EE. That's how we handle significant figures with TI calculators. I'm going to multiply that by 0.3166. And that should be my x squared. X squared is 6.9652 times 10 to the minus 11. Now, how do I take the square root of that using this calculator? The easiest way to do that is to take the answer and use the caret button here to raise it to the 1/2 power, or you can do it to the 0.5 power. Raising something to the 1/2 power is the same as taking the square root of it. So my value for x is 8.35 times 10 to the minus 6. Is that what you guys are getting for x also? What I just solved for, that 6.9652 times 10 to the minus 11 is x squared. So I had to take the square root of this to get x. And I did that by taking that answer and raising it to the 1/2 power. That's the same as taking the square root. You guys getting the same value as I am for x? So I'm getting x squared is equal to 6.965 times 10 to the minus 11. And then I take the square root of that number to get my x. Okay, so what I want to do now is solve this same problem without ignoring that minus x. All right, if I couldn't use that simplifying assumption, I would have to solve this equation. 2.2 times 10 to the minus 10 is equal to x squared divided by 0.3166 minus x. So let's rearrange this equation so that we can graph it. All right, I'm going to set one side of this equation equal to 0 so that we know that we're solving for x values where y equals 0. All right. So I'm going to move this over to the other side of the equation by multiplying both sides by 0.3166 minus x. So I get 2.2 times 10 to the minus 10 multiplied by 0.3166 minus x equals x squared. I'm going to move x squared over to the other side of the equation. 2.2 times 10 to the minus 10 times 0.3166 minus x and then minus x squared should be equal to 0. So I've done all the algebra that I need to do to be able to plug this function into my calculator as a y is equal to this. And then I just look for the places where y equals 0. In other words, the places where we cross the x-axis. So here's what that's going to look like. I hit y equals on my calculator. And that brought up my screen where I can plug in my equation. Doing 2.2 times 10 to the minus 10 multiplied by 0.3166 minus x, and then minus x squared. You can also do minus x raised to the second. It does the exact same thing, one way or the other. So now my equation is entered. I should be able to hit the graph button and get a graph. Well, that doesn't look very great at all. All right. So why does it not look very great? I'm probably looking at not a very good range here. So what I'm going to do is I'm going to use what I know about this equation to mess with the range. I know that my value for x, I know that my value for x is likely to be really, really small. But the biggest thing it could possibly be is 0.3166, right? So let's look at my window here. And right now, my biggest possible x is 0.65. So we know that x is going to be a small number anyway. Let's try an x value, a maximum x of like 0.1 and see what that does. So I hit graph again. All right, we're already looking better. Still not great though. Oh. We're looking a little better. Still not great. If x is supposed to be a really small number, let's see if we can try even like 1/10 as big, 0.01 for my x max. And graph again. All right, now we're getting somewhere. We can see maybe that we're crossing the x-axis somewhere in that space right there. There's a couple of things that we could do to zoom in even further to get a clearer picture. The easiest one of those is probably to hit zoom and then go to Z box. So I just hit enter right there. And what that does is it gives me a little tracer, and I am going to hit enter at the top and bottom corners of the box that I want here. All right. So I want to make a box from here to here, because I think in that region is where I'm probably crossing the x-axis. You guys see that? All right, still that doesn't look super great. Let's try Z-boxing again. All right, so I'm going to go zoom, Z-box. All right, still not great. So let's box in again. We're just trying to zoom in until we can clearly see the place where we've crossed that x-axis. There it is. So do you see the line on the top and the bottom of the x-axis? All right, so somewhere in there is our place where we have intercepted the x-axis, all right? A place where our y equals 0. So how are we going to find that answer directly? Your calculator has a couple of different ways to do that depending on how old it is, all right? So with this old ancient calculator, I'm going to go second function and then calculate. I think I should be able to calculate this as a root. All right. A root being a place where we cross the x-axis. So when I hit enter here, it's going to ask me for lower bound. In other words, it wants me to put in the lowest value of x to look at. All right. So right here is good because we know we haven't crossed the x-axis yet. So I hit enter. And then upper bound, it wants me to look at something on the other side of where that root is supposed to be. So about there is fine. And then I guess it's asking me, like, where do you think that actual root is? So somewhere in the middle. And I'm going to hit enter. And when I do, it gives me the root. That's 8.35 times 10 to the minus 6. Is that the same answer that we got when we ignored that chain? It sure is. Now, obviously, our newfangled graphing calculator on our cell phones is a lot easier to use because we can zoom with our fingers instead. It makes it a lot faster than having to draw a box, zoom, draw another box, and zoom, draw another box, and zoom. But we got the same place, all right? And the TI-84 pluses or 83 pluses, they have all those same tools on them. Instead of root, it may call that calculation a 0 instead, but it's the same thing. All right, let's do another one of these where we will be forced to not use the simplifying assumption. So let's do number 77. By the way, this chemical reaction is producing gaseous bleach. HOCl is, well, that is hypochlorous acid. So hypochlorous acid is kind of like what bleach looks like if you acidify it. Bleach that you get at the store is sodium hypochlorite, NaOCl. K for the reaction. .0900. And our initial concentrations of H2O and Cl2O are both 1.00 mole. What are our changes going to look like to get to equilibrium? Very good. Because for every 1 mole of this that we lose, we gain 2 moles of this. Whatever our change in molarity is here, this one has to be twice as big. So at equilibrium, those should be our concentrations. let's write our equilibrium expression here. We know that K is equal to our molarity of HOCl squared divided by our molarity of H2O and divided by our molarity of Cl2O. So we can use that equilibrium expression now and substitute everything that we know to be able to solve for X. In other words, to figure out what these three concentrations are once we know what X is. So 0.0900 should be equal to 2x quantity squared divided by 1.00 minus x quantity squared. Notice that because this and this are both 1.00 minus x, I just squared that denominator to multiply those. It'll make our calculation a little bit easier to put into the calculator that way. Does everybody understand where that came from? Okay. From here to solve for x, we use whatever technological marvels we have available to us to do that, whatever app you choose. I'll use my ancient TI-82 calculator today just to prove that it works just as well as our new cell phones do, all right? Remember that we were doing calculations much more complex than this to send people to the moon 25 years before the TI-82 calculator was first used. So they were doing these on pen and paper. We have much better tools now. So let's rearrange this equation to make it easy to put into our calculator. All right, 0.0900 times 1.00 minus x quantity squared should be equal to 2x quantity squared. We can move either one of these terms over to the other side. So something like 0.0900 times 1.00 minus x quantity squared minus 2x quantity squared is equal to 0. All right, now we have a form of the equation that we should be able to graph. Y equals to this, and then just figure out where y is 0. And that should be it. Now, our range for my calculator is still the same range that I had installed for the last problem, where my x value was really tiny. We're going to expect our x value to be bigger here because our k is not a very large or a very small number. So what are the limiting cases for our x size here? What's the smallest value x could possibly be? 0, right? If we didn't change our concentration at all to get to equilibrium, x would be 0. What is the maximum possible value for x that we could expect based on our problem? Yeah, if all of our reactants turned into products, our x value would be 1. So the cool thing is, if we are graphing this and don't like what we see, and I see nothing on the screen right now because we zoomed in too much, what we can do is set our window to what we know the right x window is going to look like. All right, our maximum value of x is probably going to be 1.00. It can't be any bigger than that. So let's graph again. Hey, look, now we see one of the places where we cross that x-axis. And it looks like there's only one here. So using the context of the problem to find the window that you're looking in for your graph is a really handy strategy. All right. When I hit window here, I know that my X value that I'm looking for is going to be somewhere between 0 and 1. So that's what I put in for those. And then when I graph, I can see the place where I'm crossing that X-axis. If we want to see a little bit more of the graph, I can always zoom and go to zoom out. And it looks like we can see more of the function now. And we can see a place where we cross the X-axis for negative values. And then I see another on the positive side. So the positive side is what we're looking for, but if we want to zoom in a little bit, we can go to zoom and then box, and then build our box around both of those so that we can see them very nicely. So it looks like this is our crossing of the X-axis that we're actually looking for. So to solve for that, I'm going to go second function and then calculate, and then go to root. We definitely want our X to be a positive number. So I'm going to hit enter really close to 0 for my X value. And then the problem is I don't know exactly where. All right, I know that I've crossed the y-axis, or sorry, the x-axis, because if you look somewhere around here, my y values go from positive to negative. All right, so I know I've gone far enough over now. I'm going to hit enter. And then my guess is somewhere in between those. And there we go. So because it uses approximations, this is as close to y as it can get, but that is such a small number for all intents and purposes that y equals 0, and then x equals 0.130. You could. I'm using the root function. Yours might have something called 0 instead in that list. Yeah, 0 is the newer way to describe the root. All right. The places where y equals 0. So if that is the case, if x equals 0.130, then at equilibrium, my molarity of H2O should be 0.870 molar. And my molarity of Cl2O should be 0.870 molar. And my molarity of HOCl should be what? Should it? Is my equilibrium molarity of HOCl X? It's 2X, right? Yeah. There we go. And we can check by substituting in those concentrations into this equilibrium expression, and we should end up getting a value of K of 0.0900. So let's do that really quick. All right. 0.260 squared divided by 0.870 squared should be our value of K. So let's check. And I'm getting very, very close to 0.090. Close enough that I know I've done a good calculation. Is it helpful to see that calculation done on one of these instead? The what? The graph inside of it, right? Okay. And putting my right down in my guess on the positive side of the graph line. And I was in like 2 like that. Well, let's look at how you entered your function in. Can I use your calculator for a sec? Wow, we're almost out of time already. Woo. I have another meeting at 3 o'clock. Actually, I have another meeting that's already started, but I can't be there until 3 o'clock. It looks like there may be a problem with how we've put, whoa, I see a cosine in there someplace. That's bad. Well, it's in there. All right, so that is definitely our issue here. We'll insert a parentheses there. You had an extra whole set of parentheses that you actually didn't need here in any place, but that's not going to hurt anything. All right, so let's graph it. Yep. All right, so now we're going to go to, this is certainly a trackable graph. We can find that 0 here. Second function, calculate. All right, and we're going to look for our 0. And I'll make that my left bound. This my right bound, and then somewhere in here for the guess. Weird. Double weird. Just reset. I wonder if it's not liking something about all these nested parentheses. Oh, it looks like you had a squared on the outside of that entire thing. There was an extra. Okay. But there was a squared out here. I think that's what was wrong. So if we go to graph, I'm going to delete another round of these parentheses. Those. Why is it double nesting this? All right. So I'm gonna delete all this, not the whole thing, but that last part, we'll put it in with one set of parentheses. It keeps on like reverting back to the weird old version. Oh no. I did not mean to push the clear button. Did you use the inverse of natural log instead of the EE button? EE is the one. E is the inverse function of natural log. Yeah, that's the inverse function of natural log. Okay.
Was really unhappy with the way that was being used.
Mhm. There was something in that last term that wasn't registering correctly, and every time I would try and just fix it and then hit enter, it like undid the fix for some reason. I have no idea. But there's no reason to over nest in parentheses. I think you had 2x quantity squared and then parentheses and then another squared on the outside of it. And it kept on re-putting the squared on the outside when I would try and fix it.
Thank you.
Yeah. So on Wednesday, we will continue our discussion of equilibrium math. We will start to talk about like a transitional topic that will take us to the end of the material for exam 2, and we'll also like have some of that covered on exam 3, which is a special kind of K called KSP, solubility product. We've already done calculations with KSPs, we just didn't call it KSP. So those are all about when an ionic compound dissolves in water to make aqueous ion. That's a KSP reaction. We'll see a bunch of them. All right, I will see you guys on Wednesday.